Hey everybody, so in this video we're going to look at modelling with reducible differential equations. In example 1 we're going to look at a first order differential equation, and in example 2 we'll look at a second order differential equation. So in example 1 we're told that a particle is moving along the x-axis and its displacement x at time t seconds is modelled by this differential equation. And for part A, we've been told use the substitution that x equals wt, where w is a function of t, to show that the original differential equation can be reduced to this form. And then for part B, we're going to find a particular solution to that differential equation, and then for part C, we'll use that equation to find velocity. Okay, so if we have that x is equal to wt, then we can find dx by dt using the product rule, where dx by dt will be the u term multiplied by the derivative of t with respect to t, so this is just w, plus the t term multiplied by the derivative of w with respect to t, so dw by dt. And now we have dx by dt, we can substitute this into our differential equation here. So we have w plus t dw over dt is equal to t squared plus the x squared, but I can substitute x as wt, so plus w squared t squared all over 2xt. But when I substitute wt into here, we get 2wt squared. Now we can simplify this fraction by cancelling out the t squared from a numerator and denominator, and we can move this w to the right hand side. So t dw over dt will be 1 plus the w squared over 2w minus this w here. But I can use equivalent fractions to give it the same denominator. So this will be 2w squared over 2w. So now I can simplify the right hand side. So t dw over dt will be 1 minus w squared over 2w. Okay, so now we have it in this form. We can begin to separate the variables so we can integrate. So to separate the variables, I'm going to move these w's over to the right hand side to be with this dw, and I'll move the t and the dt to the right hand side. So we get 2w over 1 minus w squared dw is equal to 1 over t dt. And now with the variables separated, we can take the integral of both sides. So to integrate 2w over 1 minus w squared dw, I need to use the reverse chain rule, because can you see, if we differentiate with w squared, we get 2w. So if we let y equal the natural log of 1 minus w squared, and then we found dy by dw, well, this will be 1 over 1 minus w squared, and this is what we want. But when we multiply it by the derivative of this inner function, we get minus 2w. So dy by dw becomes negative 2w over 1 minus w squared. But now I need to scale this negative so it matches our integral. So I need to multiply this y by negative 1. Okay, so our integral then becomes negative the natural log of 1 minus w squared is equal, and to integrate 1 over t with respect to t, this is the natural log of t plus a constant, and because we're looking at natural log form, I'll write the constant as the natural log of k. And now we can simplify this using the rules of logs. So this becomes the natural log of 1 over 1 minus w squared. I've just used the power rule to bring this negative to the top here. And we can simplify the right-hand side by multiplying the t and the k together. So this is the natural log of tk. And then we can take e to both sides. So it becomes 1 over 1 minus w squared is equal to tk. So at this point, we can substitute x and t back in place of w. If x equals wt, then w will equal x over t. This becomes, I'll just blot this off to keep it tidy, 1 over 1 minus x squared over t squared is equal to tk. So now we have it in terms of x and t. I can substitute in the boundary conditions. So if x squared is equal to 4 squared and t squared is equal to 8 squared, one is simplified to make 1/4. So now we have 1 over 1 minus a quarter, so 1 over 3/4, which becomes 4 over 3. T we know is 8, and this is equal to 8k. I'll divide both sides by 8, so k will be equal to 1/6. So now we have k is 1/6. I can substitute this k back into here. So we have 1 over 1 minus x squared over t squared is equal to 1/6 of t. I can simplify this by moving the division of 6 to the left-hand side and its denominator to the right-hand side. So therefore, 6 will equal t lots of 1 minus x squared over t squared. We'll multiply out the t with the brackets, so 6 will equal t minus x squared over t. We'll multiply 3 by t to cancel this out, so therefore 6t will equal t squared minus x squared, and then we can make x the subject, so x will equal the square root of t squared minus 6t. So this is our particular solution. So for part B, find the velocity of the particle when t equals 10. So we know that velocity is dx by dt. So we need to differentiate this with respect to t. So I'll write x as t squared minus 6t to the power of 1/2. And then using the chain rule, dx by dt will multiply this power down, so 1/2 of t squared minus 6t to the negative 1/2, and then we'll multiply it by the derivative of this inner function, so 2t minus 6. I can tidy this up, so dx by dt will be 2t minus 6 over 2 lots of the square root of t squared minus 6t. We can factor out this 2, so this gives us t minus 3 over the square root of t squared minus 6t. And then to work out the velocity when t equals 10, so a velocity when t equals 10 will be 10 minus 3, which is 7, and then the square root of 49 minus 42, so the square root of 7. We can rationalize this denominator, so a velocity will be root 7 meters per second. Okay? And in example 2, we're going to look at modeling with a second order differential equation. Okay, so for example 2, we're told that the concentration of a drug in the bloodstream of a patient t hours after the drug has been administered where t is greater than 0 is modeled by this differential equation, where y is measured in micrograms per liter. And we've been asked to use the substitution that t equals e to the u to transform the original differential equation into this form. So if we begin where t is equal to e to the u, and we can work out dt by du as also e to the u, which is then also equal to t. And then we can use the chain rule to work out dy by du, because if dy by du, this will equal dy by dt multiplied by dt by du, because these dt's will cancel, and then we're left with, on the right hand side, dy by du. So dy by du will equal dy by dt multiplied by dt du, which is what we found here as t. So now we have dy by du, we can find d2y over du squared by differentiating this again with respect to u. To do this, we can use the product rule. So we have dy by dt multiplied by the derivative of t with respect to u. So dt by du plus the t term multiplied by the derivative of dy by dt with respect to u. So this becomes d2y over dt squared dt by du. So I've had to use implicit differentiation to differentiate this with respect to u. We can tidy this up because we know dt by du we've found over here is t, and then we can simplify this pair by crossing out the dt's. So d2y over du squared will be, I'm going to write this bit first, so t times t squared d2y over dt squared plus dy by du. Okay, so now we can substitute these expressions for dy and dt back into here. So t squared dy over dt we have here, so we can substitute in d2y over du squared minus dy over du. Then we've got minus for 2. Well, we've got t dy by dt here, and this is simply dy by du. Then we'll add for 2y, and that will equal negative t to the negative 2. But we know that t is e to the u, so this will be negative e to the u to the negative 2. Now we can tidy this up because we can collect the dy by du term together. So d2y over du squared minus 3 dy by du plus the 2y, and we can use a power rule to simplify this. So negative e to the negative 2u, and this is what we were asked to show. So now we have it in a simplified form, we can use the auxiliary equation to write the complementary function. So m squared minus 3m plus 2 will equal 0. So therefore, m must equal 2 and m must equal 1. So our complementary function then becomes y is equal to a times e to the 1u, so e to the u, plus b times e to the 2u. I'm going to leave it in terms of u for now, so we can work out our particular integral. So if we say that y is equal to lambda, the constant we need to find, of e to the negative 2u, so I've taken this from here, then dy by du will be negative 2 lambda e to the minus 2. d2y over du squared will be, again using the chain rule, 4 lambda e to the minus 2u. Now I can substitute each of these back into this differential equation. So we can substitute this in place of d2y over du squared. So we get 4 lambda e to the negative 2u. We'll substitute this into here. The negative 3 multiplied by the negative 2 will make positive 6 lambda e to the negative 2u. And then a plus 2 lots of our y term. So plus 2 lambda e to the negative 2u. And this will equal our function here, negative e to the negative 2u. So we have 12 lambdas is equal to negative 1. So lambda must equal negative 1/12. So our particular integral then becomes y, substituting this lambda back into here, negative 1/12 of e to the minus 2u. So now we know that y will be the complementary function ae to the u plus be to the 2u minus a particular integral, so 1/12 e to the minus 2u. And we know that t is equal to e to the u. So therefore, u must be the natural log of t. And I can substitute this now back into our general solution. So y will equal e to the natural log of t plus b e to the natural log of t squared. So I'm bringing this power up using the power rule, minus 1/12 of e to the natural log of t to the negative 2. We can see these will cancel, these will cancel, and these will. So our general solution then is y is equal to at plus bt squared minus 1/12t squared. So now we've got our general solution, we can use the boundary conditions to find the particular solution. So we're told that y in our boundary conditions is 2/3. So we'll substitute 2/3 for y is equal to a. We're told that t is 1, so we'll leave it as a, plus b times 1 squared, so b, and then 1/12 times 1 is going to be 1/12. We'll move this negative 12 over to the left-hand side, so therefore a plus b will equal 3/4. We'll label this equation 1. Equation 2, we'll need to use dy by dx, which is 7/6. So if we differentiate our general solution, dy by dx we'll cancel out this t, we'll bring this 2 down, and then we'll differentiate this, and we get negative 1/6t cubed. Putting back in our boundary conditions, we've got dy by dx is 7/6. This will equal to a plus 2bt, so plus 2b, minus 4/16. So a plus 2b will equal 8/6, 4/3. And we'll call this equation 2. And we can solve equation 1 and 2 simultaneously. And we get a is equal to 1/6 and b is equal to 7/12. So then for our particular solution, we have y is equal to our a value, 1/6, times t, plus our b value, 7/12, times t squared, minus 1/12t squared. And this is our particular solution. And in example B, we've been asked to find the concentration of a drug in the bloodstream of the patient after 2 hours. So this is when t equals 2. So y will equal 1/6 times 2, so 1/3, plus 2 squared is 4, that becomes 7/3, minus 1/12 times 4, 1/48. So y will equal, working this out on a calculator, approximately 2.65 micrograms per litre. Okay? Well, thank you very much for watching. I hope you found that useful. If you did find that helpful, please like and subscribe. And you can download the full lesson and worksheet on my website, missmathematics.com. There's a link in the description below. Thanks again, and take care.